So here we have a few things that we're going to use to conduct a small demo to find how far a wheel moves as it rotates once. And also we'll use the same equipment to find the value of pi. So we have here a steel scale, reasonably straight. We have a vernier caliper. This is basically an instrument which can help us measure the diameter quite accurately, right? Then we have a flexible scale here. So this can rotate and measure around the cylinder if required. And we also have here a roller scale. This is again a flexible scale which is much more finely calibrated. Okay. And of course we have a can which is pretty uniform and therefore can act as a good wheel. And of course a pen and a pencil. Okay. Let us start by measuring the diameter of this can. Okay. So I'm just taking the caliper, and because of the way it is designed, as I close it, it will close around the biggest part, right? So that is, it is exactly going to measure the diameter. I'm going to tighten this here so that it doesn't move further. And now I can take the reading. Let us now find the circumference of the can. So we'll use this flexi scale which will roll around or wrap around the can. Keep the 0 on the white. The 0 here has a line above it which kind of coincides, and this will come down to about 18.3 centimeters. 18.3, which is nothing but the circumference. And with the vernier we measured the diameter, and the diameter was 5.78. All the measurements are in centimeters. Okay, so what is pi? Now pi is supposed to be circumference divided by diameter. So let us just do 18.3 divided by 5.78, and the answer I am expecting it to be at least more than 3. We will not get a very accurate answer. So the answer we are getting is 3.16, which is good till the first decimal. This also illustrates the difficulty in calculating pi very accurately by physical instruments, especially the kind of simple instruments that we have. Therefore, what people did was they found theoretical methods of finding it, geometrical methods of finding it, and later on they had different algorithms to get onto pi. So what Archimedes did was he basically took a circle and first divided into 6 parts. So let me show you. Here we have a circle within which we have first an equilateral triangle, which is a very, very rough expression of what a circle could be. Then we have a circle which is a square, which is slightly a better expression, and then a hexagon. So Archimedes basically started from this drawing, right? So it started from this particular drawing, and you can see that this is a hexagon, and let's say this is the center. This line is going to be parallel to this line. Join this. This is going to be the radius. This is going to be the radius. Since it's a hexagon, this angle is going to be 60 degrees. These two are equal. Therefore, this is going to become a equilateral triangle, and all the 3 sides will become R. So this is basically going to become a equilateral triangle. Now, if you assume that this hexagon's perimeter is as good as a circle, let us make an assumption that this is almost a circle. Then what is the circumference of this circle? 6R. And what is the diameter? 2R. And you get a value of 3 for pi. So from this you can calculate that pi is 3. But as you can see, it's not a very good approximation for a circle. So what he did further was he took a bigger circle and made a polygon with 12 sides. Now you can see the amount of area that is left is even lesser. Then he calculated for that, and then what he did was he doubled that. So say 24 sides, so that now it looks something like this. Now see, it's a much better approximation of the circle. And then he went on all the way till 96 sides, and came to approximate value of 3.14.